Today we have with us Professor Matthew from Georgian Institute of Technology. Welcome to the interview session, Professor Matthew. So we'll jump into the first question of the day. So we would like to explain, can you explain us the rationale behind choosing aluminium as a key component of your research?
Yes, so our recent work focuses on using aluminum foils and aluminum foils with particular microstructures for lithium-based batteries. And the reason why we're doing this is because it has been known for a long time that aluminum can react with lithium and be used as an active battery material. It can store lithium inside the battery. But aluminum has never worked very well for that because when it does store lithium in a battery, the aluminum itself expands and contracts and expands and contracts during charge and discharge, and it degrades, its performance degrades. Okay. So if we could make it work, it would be beneficial because it can store a lot of lithium. There's a high capacity, but it's been a challenge in the past.
Okay. Okay, so could you provide some insights into the design consideration that led you to the phase distribution?
Sure, yeah. So the concept here is that you start with an aluminum foil. And the way to think about this is when we charge and discharge the battery, the lithium ions are actually moving into the aluminum foil and then moving out of the aluminum foil. And you want that to be as reversible as possible. Okay. So it turns out that if you use just pure aluminum, it works okay, but what ends up happening is the lithium tends to get trapped in the aluminum and it's difficult to extract the lithium when you want to. So what we decided to do, based on some prior literature, was to make a multi-phase alloy with another material, kind of a small amount of another material distributed throughout the aluminum in a different phase. And this is beneficial because it helps a number of things, but especially it helps with improving the reversibility and the extraction of lithium so that we can get high efficiency in terms of the charge and discharge.
Okay, that's good. So your paper mentions that the alloy based electrodes exhibit less ESI growth compared to those in non-aqueous electrode solution. So could you help us with the underlying reason for this difference and how it contributes to the prolonged stability?
Yes. Yeah, an important aspect of this that I haven't mentioned yet is that these electrodes that we're using, the aluminum that we're using, is within solid state batteries. And solid state batteries are a relatively new technology that's under current development, and they could be safer than conventional lithium ion batteries. The difference between a solid state battery and a lithium ion battery is that lithium ion batteries have a flammable liquid electrolyte, which conducts the ions throughout the cell. So you replace that liquid with a solid material for a solid state battery. And so this all relates to the aluminum because it turns out that when you create a solid state battery with an aluminum based electrode material, that aluminum ends up being much more stable as well because the interfaces are more stable and the liquid just causes problems when you use aluminum in a lithium ion battery. So everything works together very well, I would say. It's a little complicated, but we found that the results were quite promising.
Okay. So your research introduces the concept of microstructure engineering for the negative electrode. Can you elaborate on the specific challenges and the strategies in designing and achieving the desired microstructure to enhance the capacity and rate behavior?
Yes, it's quite interesting actually. There's been a little work on this in the past in different battery systems, but what our work shows is that starting with a dense metallic foil material, controlling the microstructure can enable you to tailor the performance of the material. And this is interesting because it kind of opens up the door towards microstructural engineering and metallurgy for improving battery performance, which is something that hasn't been a major focus of the battery field in the past. So we hope that the promising results that we reported will will inspire others to also work along these directions. And we're excited about our future work as well in this area.
Okay. The impact of stack pressure on electrochemical behavior is explored in your research. Could you provide the insights into how different stack pressure influences the performance of alloy-based negative electrodes?
That's a great question. It's a very important variable, the stack pressure. This is basically the amount of force you're applying to the battery cell. And it's particularly important in these solid state batteries compared to conventional lithium ion batteries. So we found that in general, higher stack pressures made it easier to achieve good performance. But there was some variability when you change the stack pressure and it went to lower values. We're exploring much lower values now of stack pressure because for commercial applications, the stack pressure, minimizing the stack pressure is quite important.
Okay. That's great. So the findings of your study suggest potential cost and energy savings. Can you discuss the feasibility and challenges of implementing such a design in large-scale battery manufacturing processes?
Well, our material that is in this published paper now is an aluminum. It's 95% aluminum and 5% indium metal. And indium metal turns out to be a very expensive material. So we're not focused on indium metal for eventual commercialization. So that's one challenge. In general, though, the process that we demonstrated is quite scalable to very large foil processing sizes. The company that we're working with on this is a large aluminum manufacturer, Novelis Incorporated, and they commonly make foils at extremely large scales, especially compared to what we're used to in academic research. So, meters wide and very long, many 1,000 meters long or so. The whole intent of this work was to use processing methods that could be scaled to very large sizes from the very beginning, although we haven't demonstrated that yet. But ideally, that will be available going forward.
Okay. So your research focuses on aluminium-based electrodes. Like, how applicable do you believe the observed performance improvement would be to other alloy systems, and the specific consideration for exploring different alloy material in solid state batteries?
I'm very excited about the possibility for various metal alloys as anodes in solid state batteries for a few fundamental reasons. The main one being that they tend to be, the interfaces of these materials tend to be more stable over many charge-discharge cycles than they are in lithium-ion batteries. And so I think there's good promise going forward for alloy materials in solid-state batteries, which is good because this could enable higher energy density battery systems. And there's a lot of folks working on these materials out in the field. And I hope that there'll be some good progress in the next few years.
Okay. So looking ahead, your study identifies several areas for future exploration, including optimizing alloy composition, understanding material evolutions, and investigating the effects of other elemental additions. So if you can share your thoughts on the next steps in advancing the field of solid-state batteries through your research findings.
Yep. So we're currently investigating different material combinations, different microstructured alloys, and we're also scaling our cells to larger sizes for testing purposes. So that's kind of our next steps. I think more broadly, there's efforts in the field to develop high alloy concentration electrodes that could enable batteries, solid state batteries with high energy density. And so things are moving forward. But the process for commercialization of a battery technology is always a long and arduous path, actually. So it takes many years, and it takes quite a lot of effort to go from a laboratory demonstration to a medium scale cell to a full scale cell, all the way to high volume manufacturing. So it's important to note that there needs to be some patience in these efforts because it does take a while. But we're excited and we're moving forward as fast as we can.
Right. Okay. Okay, Professor. So that's all. That's the question that we had for today. So hope we'll meet again with
Great.
your new research findings, and we can interview a little more